Hi, I'm Masih Dami, PhD student at Pratt School of Engineering, Duke University. I want to go through my class project for MEA 716 about sensitivity of vertical motions over complex topography to terrain data resolution in weather and research, forecasting model, or WRF. Uh, The first motivation to start this project is a paper by Nastrom and Gage about climatology of atmospheric wave number spectra. Uh, this study shows that the kinetic energy of horizontal turbulent velocity is higher over land than over the ocean. Topography is important in the numerical weather prediction. Localized extreme rainfall events causing landslides, debris flows, and flash floods are usually associated with orographic enhancement. In addition, on global scales, the global angular momentum budgets are reported to be sensitive to terrain resolution. Before I move on to my science questions and hypotheses, I want to explain how I do spectral analysis here. This figure shows the domains that are used in my numerical simulation. There are three nested domains with different grid spacings, 12 kilometer, 3 and 1 kilometer. For spectral analysis, I extract one line of data from the outputs. I used the terrain heights in the model and the vertical velocity for the fourth eta level of the model. The spectral analysis are for a line of approximate latitude of 35.87. There are four different options for the terrain in WRF that are 30 seconds, 2 minutes, 5 and 10 minutes terrain resolutions. I am showing the terrain height for the 10-minute data and 30 seconds data and their differences in the first row. The terrain is smooth in the 10-minute data, while you can see small scale features in the 30 seconds data. The ridges are typically represented higher and the valleys are lower in the 30 seconds data. In the second row, the spectra of the terrain for three different domains and three different datasets are shown. For domain 1, the three terrain options make almost identical spectra, but for domain 2 and domain 3, with finer grid spacings, you can see a different scaling behavior in the spectra. In addition, the way the terrain is interpolated in the model make a difference in the behavior of the spectra. My main science question in this study is how does the parameterized turbulence and resolved grid scale motions change with the topography in the model. In general, for an idealized parameterization, the total resolved and parameterized variables in the model should be independent of the grid spacing. Another question is, what is the proper choice of terrain data resolution for a given model grid spacing? And as a suggestion, if there is a scale invariance, it can be used while interpolating the terrain data to eliminate resolution dependencies. The simulations are done using the WRF version of 3.71, and three nested domains focus on southern Appalachian mountains. The rest of the configurations are based on the typical model runs in research papers, specifically Wilson and Barras, 2015. Cumulus scheme is only on for the parent domain. Simulations are from May 12 to May 16 that are associated with a clear sky case in the first 3 days and a cold front passing through the domains in the last day. The terrain options are shown in this table. As you can see, I've crossed the 2 minutes case because it crashes for some reason after a few hours of simulation. I also saved the continuous time series of output variables for 2 points. One of them is University of North Carolina, Asheville, UNCA, that is in a valley, and the other one is Mount Michel, that is on a ridge. The green box shows the model elevation for the 30-second terrain, and the red box is for the 10 minutes terrain. The differences are up to 600 meters. Now we're looking at the time series of sensible heating for these two different stations. The first row is for UNCA and the second row is Mount Michel. The light blue line is for 30-second terrain and the orange line is for 10-minute case. We have the plots for 3 domains, 12 kilometer, 3 kilometer, and 1 kilometer. There are some fluctuations in the time series that may be due to different types of clouds passing through different simulations. Also, there is a noticeable difference for domain 2 and domain 3 that are explainable when we look at the latent heat flux. Now we are looking at the time series of latent heat. You can see for the domain 2 and domain 3 of UNCA, we don't have latent heat flux for the 30-second terrain data. And that is, I believe, because the land use also changes when we are changing the terrain data. So the latent heating is shut off at that point, causing the sensible heating to increase. Now we are looking at the vertical velocity spectra for domain 3. The plots are for 2 different days and 2 different times of the day, 1 a.m. local time and 1 p.m. local time. The red lines that are shown on the spectra, those are for 2 delta x, and the line on the left is for half of the length of the domain. As you can see, the blue line, which is associated with the 30-second terrain, is consistently higher than the other 2 lines that are associated with coarser terrain data. Next, we are going to move to domain 1, and you can think of domain 2 as a transition between domain 3 and domain 1. The spectra for domain 1 are almost identical for 3 different terrain data. The slight differences between the spectra may be due to the fact that the nesting is 2-way, so domain 1 is interacting with domain 2 and domain 3. I'm showing the spatial plots for differences in the temperature field and incoming short waves for between the 30-second terrain and 10 minutes terrain. The first row is the temperature field and the second row is for the short wave. The first column is for a time before the sunset. As you can see, the temperature field follows a similar pattern to incoming shortwave. I believe that differences for the incoming shortwaves that are up to 118 watts per meter square are due to the fact that we have shadow and we have different slopes in the model. And specifically at that time, shadows are very important. In the second column, we're looking at the 1 a.m. local time. The differences in the temperature field are up to 5 or 6 degrees. I believe the differences are because we have different clouds in the model, and hence we have different long wave radiation. And of course we don't have incoming short wave at that time because it's during the night, and the last column is during the day, 1 p.m. local time. The differences are less compared to the other two. Next, we are looking at the parameterized TKE fields, the differences in the parameterized TKE fields for 3 different days and 2 different times of the day. During the night, differences are very small, while the differences during the day are higher. The absolute values for total kinetic energy is about 2 meters square per second square. So we can say the differences in the TKE field are up to 50 to 100%. Also, May 13th and May 14th, they show a similar behavior, and May 15th is slightly different because that's associated with a day that the front is passing through the model. Next, we are looking at the sensible heating, the differences in sensible heating for 2 days, 2 different days, and 2 different times. Again, I believe they show a similar pattern to TKE. There are high differences during the day. The differences at night are smaller, and locally, some of the differences are very high, up to 300 or 400 watt per meter square. That I believe is due to the fact that we have different land use properties, and we're looking at the same plots for latent heat flux here, and you can see almost same behavior as sensible heating here. Now we are looking at the accumulative grid scale rainfall. I'm trying to compare the 10 minutes simulation and 30 seconds simulation for 2 different days, May 15th and May 16th. For the case of May 15th, the differences that we see is mostly about orographic clouds, while May 16th we have a front passing through the domain, so the differences are for synoptic scale forcing rainfall. The interesting point is that the terrain also affects the larger scales rainfall. The differences are up to 50 millimeters here. So in conclusion, shortwave and temperature field at above 2 meters from the surface follow the landform pattern and are strongly different at certain times of the day. TKE varies significantly with terrain data, sensible heating, and latent heat flux. They also show a similar behavior. Precipitation pattern is also changed considerably. In addition, I believe that larger time-scale phenomena such as diurnal cycle, triggered convection, or climate models may be even more affected by the terrain data. So, I think we should think about not using the default terrain that is available in the model. Thank you for watching.